When you open a graph editor and press the Tab key to type global variable, you will find a get and set global variable node for almost every graph type. We have created these get and set global variable nodes to fill one specific need, sharing data between different graphs. The get and set global variable name is similar to the name of the functions available in the Python SDK. However, the data is stored in a different location, so unfortunately, it is not possible right now to share data between Python and graphs. Before watching these nodes in action, it is important to understand how data types are handled in RealFlow graphs. There is a tutorial dedicated to explain data types in RealFlow graphs. For the moment, I will only remind that there are two groups of data types according to how they are stored. Basic data types are stored by value. These types are the number types, real, integer, integer 64, vector 3, matrix 4, quaternion, plus the string and box types. Unless it is explicitly marked in the node with an internal connection, this data is copied after every operation performed on it. Complex types, on the other hand, are stored as pointers or references. This means that when you perform operations on complex data, you will be modifying always the same object. One array in the graph might contain several references to the same data. Therefore, if you apply an operation over that array, the operation will affect the data as many times as the number of references in the array. If you need to duplicate the actual object behind the reference, you can use the existing copy nodes. Once you know how types work, you are ready to create the first setGlobalVariable node. Let's try first with a basic type, an array of integer numbers. For storing integers, we need the setNumGlobalVariable node. SetGlobalVariable nodes feature 3 inputs and 2 outputs. The first input is the name of the variable. The name is used as the key to store the data into a global dictionary. There is a separate global dictionary for every data type. This means that you can repeat variable names as long as they are from different types. Variable names are also case sensitive. After deciding the name of your variable, you have to decide if it will be stored as a copy or as a reference. Storing it as a reference means that wherever you access the global variable, it will act like if it were directly connected to the source of the data. Of course, this doesn't mean that when you request the variable from another graph, the graph execution will continue on this one. It means that if you remove the original node, the data will be no longer available in memory. If you store it as a copy, the data connected to the input in is duplicated in global memory and completely independent from the original. The setGlobalVariable node has 2 outputs. The through output, like in every node, represents a direct pass-through of the original data incoming to the node. The outCopy output returns exactly the same data that you would get if you create a getGlobalVariable node to get that variable. If the storeCopy input is set to false, both outputs will return the same data. Let's see a real-world example. I will create a 5-element array containing a real constant. Let's say 2.5. Then I will store it as a reference instead of a copy. Now, after executing it, you can access its data from any other graph in the same RealFlow instance. I will create now the getNumGlobalVariable node without providing too many extra details. Let's check the size of the output of this node. To check the size, we can add an array size node connected to a message print. As you can see, the size is the same. But now, let's see what happens if I remove the node connected to the setGlobalVariable node. If I execute the graph again, now the size is 1 instead of 5. A 1-element array is the default value when data is missing for numbers. I could have also purged the first graph, but I wanted to make clear that the node responsible of releasing the data was the constant array one, and not the setGlobalVariable node. Let's bring the constant array node back and store its reference in memory again. And this time I'm going to use a negative value for the constant. In my other graph, I will compute the absolute value of this global variable. Instead of printing the size, I'll print the result. It's a positive value. Now, if you access to this very same variable anywhere else, you will notice that its value has changed. Let's duplicate this graph and keep only the messages with the result. And there we go, the value is positive. This is probably what one would expect since we are storing a reference to the data. Freedom of access and modification anywhere. It's time to check the same examples when we store a copy instead of a reference. We only need to swap the input value of the setGlobalVariable node and execute the graph. After this modification, we can already remove the constant array node. You can see how the data remain in global memory. Finally, let's see what happens if I modify again the content of the array. As you can see, the data stored in global memory has been modified. This is because the difference between storing a copy or a reference does not affect the way the data can be accessed. It only affects the way it is stored. If the data is too big, sometimes it doesn't make sense to create an extra copy to be stored in global memory. That's one example where storing something as a reference instead of as a copy is a better choice. Before focusing on the getGlobalVariable node, there are a couple of things I'd like to mention about the global memory. When you click on the purge button of a graph, all the nodes of that graph release their allocated memory. However, data stored in global memory using the setGlobalVariable node in copy mode remains there. Right now, there is no way to completely remove a global variable. When you overwrite a global variable which was stored as a copy, RealFlow will release first the previously stored data. Right after that, it will replace the entry in the global dictionary with the new data. Therefore, if you want to force a deallocation of something stored in global memory, you can simply overwrite that variable with empty data. For the same reason, right now it is not possible to measure the exact amount of global memory being used by your graphs. Now it's time to explain the getGlobalVariable node usage. The aspect of this node is simpler than the setGlobalVariable one. In this case, the only input is the name of the requested variable. The output represents the access to the actual data stored in global memory. You can access variables that have been stored in the same RealFlow instance. If the variable you try to request is not in the global memory dictionary, the getGlobalVariable node will display an error. Let's see that in action. Okay, I'll clean that error message. In this case, the output is an empty value. There is one thing you need to keep in mind when mixing setGlobalVariable and getGlobalVariable nodes in the same graph. You should never try to replace a global variable with the exact same data it is already storing. The problem with this is that, As I said previously, the current data in global memory is released before updating its value. This means that RealFlow will release the very same data that you are going to set as the new data value. As a result, that data will be completely removed. We will try to improve this mechanism, so in next versions, you shouldn't have to care about this anymore. Now that you know how to use the get and set global variable nodes, let's see some useful examples of them in action. Graphs can live at any stage of RealFlow pipeline, like the beginning of the simulation, the end of a simulation step, the end of a frame. When your graphs are spread all over the place, it is very helpful to define the most important parameters all together. In this example, I will create a graph that highlights the particles of an emitter whose vertical positions are below a certain threshold. First, I need to get the emitter particles. Then, test the y component of their position. And display only the points below a certain threshold. I will increase the size parameter to make the points more noticeable. Here is where I set the emitter, and here is where I decide the height threshold. I will create a couple of emitters to see the effect. Let's save this scene and simulate. It works as expected, but I think it would be better if we could set these parameters right after the beginning of the simulation. In order to do that, I'm going to copy these two nodes and paste them in a new graph inside the simulation begin stage. Now, I'm going to create a couple of set global variable nodes, one for each of their types. After doing this, I need to go back to the other graph and replace the former nodes to use the global variable functionality. Then, if I simulate again, we can see that the behavior is the same. From now on, you can change all the parameters in the same graph and watch the results. Actually, you could create a compound with just a single input pin because the height would be resolved inside. On this second example, I will split a graph into two. The basic setup comes from the demo scene called Apply a Statistical Spectrum. It is quite simple, but I will separate the top half from the bottom half. To preserve the functionality, I will use the get and set global variable nodes as the necessary bridge between them. I don't store the mesh as a copy because I don't need the tessellated mesh to be duplicated into global memory. I can simply use the already existing data. Then, I copy and paste the bottom half in new graph, and create the get mesh global variable node. There you go. A graph that contained a single evaluator has been split into two. Sometimes, especially with simulations, the result of your operations depends on their current state. Many data is already transferred between frames or steps within the particles or the meshes in the scene. However, you might have additional data of interest in your graphs, and to carry it from one step to the next, you usually would need to at least save it to disk. In this example, I will avoid writing to disk thanks to the get and set global variable nodes. I will create an image and then I'll blur it progressively over the simulation time. Just give me a second to prepare the graph. At the simulation press stage, I will set up the initial image state. First, I will create a black image. I'll set its resolution to 1K. And then I'll paint a white circle in the middle. I want to save the result in the images folder inside the project location. This part is a bit more complex just because I need to compose the image file path. First, I load the current frame image. Then, let's add the image Gaussian blur node. let's set the radius to 2. The image needs to be stored again to be used by the next frame, so let's compose the next frame file path. And finally save it. Okay, sorry for the necessary time to build the initial graphs. If I simulate this scene, the images folder will have one output image per frame. The total simulation time has been 11 seconds. Let's see what you need to do to access the image between frames without loading or saving any file. At the simulation press stage, let's add a setImage global variable node. The name of the variable will be image. Now, in the frames per graph, we can get rid of almost everything except the Gaussian blur node. And we only need to add the getImage global variable node to access the global image. The name of the variable was image. And I will also add a last graph at simulation post to save the result image so we can compare it with the last execution. I will take that portion from the simulation pre-graph. Let's simulate again. There it is. The image is exactly the same as the last one. And the simulation time has been reduced to 6 seconds. That's close to 2 times faster. This scene works mainly because the image type is a complex type in graphs. That means that images are stored as pointers, and we are always accessing exactly the same image we have created during the simulation pre-stage. We have already seen that using the global variable nodes can improve your simulation times. In this last example, I will demonstrate how to take full advantage of it. Like in the first demo, I will create a scene that highlights particles within a certain area of interest. However, in this case, I will use a high polygon geometry for the test instead of basic world coordinates testing. For this scene, I will have imported the Stanford Dragon model. It's composed by over 800,000 triangles, and I already catched a simulation with about 100,000 falling particles. Let's create our graph at the frames post stage. First, I will compute the distance field of the import geometry. Later, I will check if the particle lays inside or outside depending on its distance sign. A negative value means the particle is inside. Positive values represent the outside volume of the object. Instead of simply clicking on Simulate, I will first move some frames later the timeline. Now let's execute the graph only once. The graph apparently works. It's better to hide both the domain and the dragon to see the results. It takes a bit long. We can have a look at the execution time rank. The computation of the distance field takes a big amount of time, and this graph is going to be executed for every frame of the simulation. Let's let it run for 50 frames before coming back. Okay, the whole thing took almost 10 minutes to complete. So, how to optimize the process using the get and set global variable approach? Since the dragon model is static, we are going to compute the distance field only once. Let's just copy and paste the portion in the new simulation paragraph. And this is where we are going to create the set distance field global variable node. The amount of data is big enough to not make a copy in global memory. The only remaining task is accessing the already computed distance field for every frame. Let's create the get distance field global variable node. Again, the graph looks even simpler thanks to that. We can simulate this scene at last. It took 34 seconds this time. The numbers speak for themselves. The performance gain is huge, but that's not all. we could increase the precision of the distance field. Let's have a look at the distance field we have been computing so far. It's as simple as adding a new display field scalar node. To be honest, its resolution is quite small. You can reduce the cell size to increase the resolution of the field. If we recompute it again, it takes a bit longer. However, it looks much better. Let's simulate 50 frames again. The whole process takes now 45 seconds. In summary, using the get and set global variable nodes, we have been able to make our test 5 times more precise and still 13 times faster.